This video is going to be exploring the concept of quantum numbers. And so one thing I want to kind of make perfectly clear at the beginning is I've seen a lot of students kind of fall into a pit hole with some of these values. But the main reason why you're going to run into some issues is just because you're going to be overthinking these concepts. And so first things first is, what are these quantum numbers? And so the first quantum number that we are going to be referring or discussing is going to be what they call the principal quantum number. So the principal quantum number is represented by the symbol of n. And so you can kind of think about this in a very similar light as Bohr's orbits, but keep in mind these things are not just orbits. These things are going to be some funky looking shapes that we'll discuss later on. And so n is basically the orbital energy, or reference is the size of these orbitals. And so whenever I mean size, I just mean the smaller the value of n, the smaller these actual orbitals, and the closer these electrons in those orbitals are going to be to the nucleus. And so the next quantum number is what they call angular momentum quantum number. And this is represented by the symbol of L. And so in these cases, your L can only be, can only go as high as your principal quantum number will allow it to. And so your angular momentum quantum number is going to be restricted to the values of 0 all the way up to n minus 1. And so whenever I say all inclusive, I just mean the fact that every single one of those numbers has to be included. And so it's not just going to be 1 and 2 and 3. It's going to be all of the values from 0 all the way up to your n minus 1. And so right now it sounds kind of silly, but I'll kind of discuss this more later on in this chapter, is this value represents a letter, which then represents a shape. And so the crazy thing about all these quantum numbers is you're basically going to be figuring out a number that is represented by a letter that stands for another letter that stands for a shape. And so whenever I talk about this SPDF, those are the shapes in which your orbitals can exist in. And so this last quantum number we're going to talk about right now is called the magnetic quantum number. That's represented by the symbol of M sub L. And so that M sub L also has restrictions on it. And those restrictions are going to be only dictated by whatever values that you're going to be looking at for L. And so your M sub L can equal your negative L all the way up to your positive L. And please note here, I'm still telling you that this is all-inclusive, meaning the fact that all of these values must be included. And so the magnetic quantum number talks about the orbital's orientation. And so just again, please check out your book for these shapes and how they're actually drawn. But the s orbital is going to be a sphere. And so for a sphere, you only have one way you can orientate a sphere and it still look like a sphere. But these p orbitals, they actually are what they call dumbbell shape. And so you can have a dumbbell shape that is standing up, and so it's kind of along the horizontal axis, or you can have a dumbbell shape that is laying on its side, or it can, again, along the vertical or horizontal axis. And then you can also have the dumbbell shape that looks like it's coming in and out of the screen, or that's going to be along the z-axis. So the main thing that you need to memorize about this table that I have here basically is you need to understand the restrictions that you can place on the L's and the M sub L's in order to make sure you come out with the correct values. The L's, as I mentioned earlier, represent these shapes. And so when you talk about an L equals 0, that is referring to the s orbital shape. Whenever you have an L equal to 1, you are referring to a p shape. When L equals to 2, you're looking at a d orbital shape. And when L equals to 3, you are looking at an f orbital shape. Please note, I started at 0, not 1. And so here, because the limitations that you're going to be putting on your L's is going to be 0 up to n minus 1, your s orbital needs to start at 0 and not 1, or it's going to throw all your other work off. And so when you start reading through and all this stuff, one thing you kind of probably came across before you started studying this table is the whole idea of Heisenberg and Schrodinger. And so Heisenberg and Schrodinger were physicists that back in their day came up with some really, really complex ideas along with Einstein But the great thing is I've already kind of told you everything you need to know about them. And so you do not need to memorize any of the equations. And again, don't even look up Schrodinger's equation until, again, you're into like upper division chemistry, because it'll freak you out. And so main thing that you need to know about those two guys, as well as Einstein, is if you solve for those equations that I'm not going to show you, but if you solve for them, the answers to, or I guess the results to those problems will give you a probable location of the electron. Please note, probable is a word that I am putting a lot of emphasis on. I am not going to tell you the direct, exact location of this electron, because there's no way for me to actually determine that. And so one thing you have to understand about electrons is they're really, really fast. And so if you think that you know where an electron is going to be, it's no longer going to be there because time has passed and the electron is somewhere else now. And so in these cases, the closest you can get is a probable location of these electrons. And by that, I mean, I can probably tell you the location, like the neighborhood in which this electron hangs out, but I can't tell you exactly which house that electron lives in because, again, it's rarely ever there. It's always running around that neighborhood. And so if we have a value like n equals 4, then for our L's, we again can have the restriction set that our L has to equal 0 all the way up to n minus 1. And so for n equals 4, we're going to have L equal to 0, 1, 2, and please note I say and 3, meaning the fact that all 4 of these values have to exist in the n equals 4. And so because of that, I'm telling you that if you're in n equals 4 or the 4th energy level, you can potentially have the shapes of the s orbital, a p orbital, a d orbital, and an f. And so the next thing you have to understand is these m sub l's exist for every single one of these l's. And by that I mean L equals 0 has its own set of m sub l values. L equals 1 has its own specific set of values for m sub l. And so your m sub l is not just one number or a collection, or even just one collection of numbers. Because you have multiple L values, that means you have to have multiple sets of your m sub L values. And so here, for your m sub L of just L, because again, your m sub L's are going to go from negative L to plus L. So if your L equal to 0, you can go from a negative 0 to a positive 0, which those don't exist, so you're just stuck at 0. For your m sub L equal to 1, you can go from negative 1 to positive 1. But please note it's all inclusive, and so it has to include your negative 1, your 0, and your positive 1. Same deal with your L equals 2. It's going to go negative 2, negative 1, 0, plus 1, and plus 2. And last but not least, for your m sub L for your L equals 3, it's going to go negative 3, negative 2, negative 1, 0, plus 1, plus 2, plus 3. And so one thing I want to kind of point out about this is if I were to ask you how many orbitals there are for your n equals 4, then you would have to include all of this information. Or in this instance, you would have to say that for your m sub l's, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 orbitals. Because for each 4 of these shapes, you can have different orientations or different orbitals available. So this is what we refer to as the sublevel. But if I were to say how many electrons exist in the n equals 4 and L equals 0, then again, you would only be looking at n equals 4 and your L equals 0 only has one chance or one option in terms of orbitals here. Or if I say if your n equals 4 and your L equals 3, then again, I'm saying that your n equals 4, for your L equals 3, you have 1, 2, 3, 4, 5, 6, 7 orbitals available. So for each one of these additional pieces of, I guess, restrictions I put on it, it's just kind of narrowing down the location of your electron. It's basically kind of saying how many people live in Texas. That's a lot of people to narrow down. But if I were to say how many people live in the north side woods of San Antonio, Texas, that narrows it down. And so you can kind of, again, start looking a little bit more specifically at that specific region instead of all over the state of Texas.